Okay. Chapter 4. Yeah. We're going to deal with the definition and properties and applications of determinant. Section 4.1 deals with the definitions and properties of determinant. Okay. This concept of determinant was introduced 150 years before the use of modern matrix, the concept of matrix. And the concept of matrix and the method of solving system of equations by using an inverse matrix was introduced by J.J. Sylvester in the 19th century. Where the determinant is used to check if an inverse of matrix exists or not. This determinant can be used to find the area, volumes, and equations of lines or equations of planes, etc. In this chapter, we first define the determinant and review its properties. Then we study how to compute the determinant by cofactor expansions. And Cramer's rule will be covered. And in the last section, in the chapter 4, we will introduce eigenvalues and eigenvectors, which is the most important concept in linear algebra. Okay? Arthur Cayley had great contributions in the early research on the theory of matrix. And chapter 4.1 deals with the definition of determinant. Okay, now we introduce our determinant function, which assigns any square matrix A to a real number f of A. Okay. Here, in order to do so, we define the concept of permutation first. Okay, for a set of natural numbers from 1 to n, a permutation on S is a 1-to-1 function from S to S. This permutation is a function, 1-to-1 correspond 1-to-1 function. So there are n factorial different permutations of S, which is a set from 1 to n, natural number. Because fixing the position of the first element leaves the n-1 factorial possibilities to permute the last. So n times n factorial, which makes n-1 factorial, which makes n factorial as a full possibility of those 1-to-1 function. Okay? So we simply denote a permutation sigma as sigma of 1, sigma of 2, up to sigma of n, which can be written as I1, I2, In, like this. Okay, I will write down on the board. Okay, so as you see, the permutation can be written in this way simply. So as a permutation sigma is a 1-to-1 correspondence, so the range is simply a rearrangement of the natural number from 1 to n. Hence, there are n factorial permutations on S. So we denote set of all permutations of set S by Sn. Then, when n is equal to 1, then Sn has only one element. 1 goes to 1. That's it. S2 is a then there are two choices. 1 goes 1, 2 goes 2, and 1 goes to 2, and 2 goes to 1. So there are only two permutations, two factorials. For 3, 1 to 3, then 1 to 3 goes to 1 to 3, 1 to 3 goes to 2, 3, 1, 1 to 3 goes to 3, 1, 2, and 1 to 3 goes to 3, 2, 1, like this. So we have how many? 6, which is 3 factorial. For S4, then we have 4 factorial permutations, which is this. just a rearrangement of four numbers, four natural numbers like this. And for S5, we have 5 factorial permutations of this type. Okay, now new definition for inversion. In permutation, an inversion is the case when a bigger natural number placed on the left-hand side of the smaller natural number. For example, if we have a 1, 4, 2, 3, then the original was 1, 2, 3, 4. Now there was a permutation change like this. So in here, 4 is in front of 2, and 4 is in front of 3, which is a smaller number. So 4 has how many? 2 inversions. Okay, like this. So 4 has 2 inversions, which is 4, 2 and 4, 3. So it has 4 has 2 inversions, because if we change once and twice, then it will be 1, 2, 3, 4. Okay, number of inversions for JK. So for one number here, we can count the number of inversions in this way. After K plus first index, the number of indexes which is smaller than K's index JK is called the number of inversion for JK. So in this case, number of inversion for 4 is 2. Okay, because there was a 2 inversion for 4 in this case. In the above example, the inversion number was 2 of 4. For 4 is 2. The number of inversion for a permutation, the number of inversion for whole permutation is the total sum of each number of inversions for J1, J2, Jn. Okay, total number, sum of the number of inversions for each Jk. Okay. So with those concepts, we define the even permutation and odd permutation. If the total number of inversions for a permutation is even, then it is called an even permutation. If the number is odd, then it is called an odd permutation. Okay? Okay. So, I explained it a little more on those concepts, and we see some examples. Here, determine whether the given permutation is even or odd by computing the inversion numbers for a permutation, sigma, here, in S5. So here, check it out. For what's the number of inversion for 5? So 5 is the 1, 2, 4, 3 are all the smaller number which is in the left. So 5 have the inversion 4, but for what 1 is a 2, 4, 3. There is no bigger number on left and right. So it's the 0 inversion for 2. For 1. For 2, there's just 4, 3, which is our bigger number. So 2 has no inversion number. And 4 has 3 on the right, which is smaller. So 4 has 1 inversion. 3, there's nothing. So there's no inversion. So we have 4 inversions for 5 and 1 inversion for 4. So we have a total number of 5 inversions for whole permutation sigma. So 5 is the odd number. So we call this sigma is an odd permutation. That's it. Okay. Here, we can check it in here. We can check here. What's the inversion number for this permutation? Here, 1, 2, 3, 4, 5. There are 5 permutations. 5 permutations. And there are 5 permutations. Then what's the number of inversions on that permutation? What's the number of permutations? What's the number of this permutation? 5. So it's an odd permutation. If we have 7, 6, or 8, and 7 here, then what will be the number of the inversion for this permutation? That will be 8, like that. So if we give any permutation here, then you can easily find the number of inversions by hand or by the tools. Yeah. If you check it, whether it is even or not, then it's an odd permutation, so it should be false. Then now we define a signature function. Signature function is this. So signature function is a function assigns each permutation of Sn to either +1 or -1, like this. If sigma is an even permutation, then signature of sigma is +1. And if sigma is an odd permutation, that assigns -1 for that permutation. With this, for S3, we have 6 permutations like this. Then here, if you count the number of inversions, there is 0 inversion, there is a 2 inversion, one which is 3, 1, and 2, 1. There are 2 inversions. And here we have 2 inversions. Here we have 1 inversions. Here we have 1 inversions. Here we have 3 inversions like this. Okay? So more important thing is here we have 3 even permutations, and here we have 3 odd permutations. Half is even and half is odd. That's very important. Similarly, for S4, we have 24 permutations, and half of it is an even permutation, and half of it, which is 12, is odd permutations. Now, this is a very important property. If tau be a permutation by switching any 2 numbers from a given permutation sigma, if we have a sigma permutation, if we change 2 numbers from there, let it be tau, then the signature of tau is same as minus signature of sigma. If you change 2 numbers, then it changes the size. It changes the number of permutation from odd to even and even to odd. Here is the definition for the determinant, finally. With all those concepts that we have covered, and the determinant function is defined in this way. Determinant of A for n by n matrix is the product of all of these, A1 sigma 1, A2 sigma 2, n sigma n, times signature of that sigma, and add how many? N factorial terms, because we have how many? N factorial permutations there. So we choose, what this means is we choose one entry from each row and columns without overlap, and give us, multiply all together, and give us signature on it. Then how many do we have? We have n factorial of those, and add all those n factorial terms like this to have a determinant. Here, for 1 by 1 matrix, the diagonal entry itself is a determinant. Okay. Here, what it says is this. Each term in the determinant is from the matrix A by choosing a row and a column without any overlapping, then multiplying them and assigning a corresponding signature. Okay. Here, find, for example, find the determinant of A. Then from A, here we choose, so A is a 2 by 2 matrix, so S2 is 1 to 2, 1. So signature of sigma 1, let's say sigma 1 and sigma 2 here. And the signature of sigma 1 is 1, signature of sigma 2 is equal to -1, because there's 1 inversion. So determinant of A is a sine of this plus sine of this, like this. So here, this is a plus A1 sigma A11, A22 plus minus A12 times A21. This is what it says like this. This can be done by this way. Just A11 times A22 minus A12 times A21, which is this. This is called the Serres method. You can check the concept of Serres here. For 3 by 3 matrix, if we have this, we have 6 permutations like this, and 3 of them has a +1 sign, and 3 of them has a -1 signs like this. Then determinant of A has 6 terms like this, and addition of, I multiply all 3 terms from each row and columns like this, and multiply them, and give the signature on these 3 terms, and give the signature for these 3 terms as a minus. So this is the determinant for 3 by 3 matrix. This can be done by just multiplying this plus product of these three two, minus product of these three, minus product of these three, and minus product of these three. Like this is called the Seller's method. But so you can find the determinant of this matrix and this matrix by using that definitions. Okay, and also you can have the determinant by giving just this comment on stage. The important thing is here. That Seller's method cannot apply. It cannot be applied to the case of degree 4 or higher. The reason is if we have a 4 by 4 matrix, then we have how many permutations? We have 24 permutations. But for 4 by 4 matrix, we cannot find 12 combinations of 4 numbers from each row in the way that we did on the Seller's method. So that does not work. Seller's method does not work for any bigger matrices. So we should, it is more effective to study the property of the determinant and find the determinant by using these properties. First property, square matrix and its transpose has the same determinant. It can be easily verified from the property, the definition of the determinant, which can be found in here. For example, if the B matrix, for the given matrix B, determinant of B is 240 and B transpose determinant is also 240. This works for any matrices. You can find the matrix and the determinant and the determinant of the transpose as well. Next, if let B be a matrix obtained by switching 2 rows from a square matrix, then the sign changes only. On the determinant, only the signs only changes. The reason is from the definition. If we can choose the matrix B like this, then it can be written in this way. And then we did change the permutation of here, the 2 numbers from here, and then that may gives a different permutation here that gives us this. So this permutations changes, so signature of sigma changed. That gives us the minus determinant of A. Okay. This comes from the theorem 4.1 because we did choose to change the signature. So sign of this been changed. It's from plus to minus to minus to plus. So as you see here, if the determinant of this is 7, then if we change the 2 rows, then determinant is going to be a negative of the previous one. So this works for everything as well. If the square matrix has the 2 identical rows, then it always the determinant is equal to 0. You can easily find if you have 2 identical rows, the determinant is 0. If a square matrix has a row with the identical zeros, then determinant is always 0. It's easy because in this case the determinant of this is a summation of these terms, but every term should choose one from the last row, which are all zeros. So all terms has zeros in it. So product of these are all zeros. So the addition should be the 0 as well. And let B be the matrix obtained by multiplying k times the row of square matrix A, then it's just simply the k times the determinant of the original matrix, like you see here. If it's A equal to 3, then if you can subtract 2 from here. You can extract 3 from here to have 2 rows, 2 columns 0. So determinant is 0. So every theorem that we mentioned is work not only for the rows and works for the columns as well. Okay, square matrix has 2 proportional rows, then determinant is equal to 0. If it's one row is a scalar multiple of the other, then determinant is 0. Most important thing is this last one here. If let A be a square matrix and K times of one row is added to another row of A, then this new matrix, say it as B, then the determinant is same. If we do the third type elementary row operation to a matrix, when we find the determinant, it does not make any change on the determinant value. This is very important because it comes true, because here we have two same rows in here, so this becomes a 0, so it's only the last part which is the determinant of A is left. So determinant of B is same as determinant of A if we do the third type elementary row operation on A. Like here, if we multiply 4, and if we multiply 2 on the second row and add to the first row, as you see, the determinant does not change anything like this. Same work for them. And for the triangular matrix, the determinant is just a multiple of the main diagonal entries. So this is the key. Okay, this is how to compute the determinant. So you use the third type elementary row operation. Simplify it as much as you can. Make it almost, and then use the properties of determinant to, or use the Serres method to get the determinant. For example, if you have this matrix, then you just simplify it as much as you can, and use the properties of matrix to keep recording it. And then this is a triangular matrix, so the determinant of this is 1, so determinant of A is 165 like this. So, and this is what this means is do the elementary row operation means you do multiply the elementary matrix on the matrix. So what this means is the determinant of EA is equal to determinant of E times determinant of A. This is what this example says. So determinant of elementary matrix here, this is actually what you already know. E is obtained by multiplying K to a row of identity matrix, then determinant of that matrix is K, and change the row, make the sign change, and third type elementary operation does not make any changes. Okay, and this is what we mentioned. Here, from here, if A is invertible, then if and only if determinant of A is not 0, and determinant of AB is equal to determinant of A times determinant of B. So from here you can check these properties with this comment. You can find the determinant of AB and the determinant of A times determinant of B. Compare these two, and they should be same. And from here, square matrix, if it is invertible, the inverse matrix of determinant of inverse matrix is 1 over determinant of A, which directly comes from the bottom. And this last example shows how you can find it. From the matrix A, you can find the determinant. If you can find the determinant of inverse, then you will see the reciprocal. I think that's the end of section 4.1. Any questions?